Hello, it's Keith here, and this is lesson 61 of the platform-specific series of my 650 assembly program tutorials, and it says Z80 there. We're looking at the Atari Lynx today, and we're looking at my multi-platform minimal tile map known as Mintile. This is a simple example piece of code that allows for a tile map simulated sprites using the same tile code, and it allows for X-flips, so we can turn our character around horizontally but not vertically. Now we're going to be looking later on at a more advanced version called Maxtile, which is my successor to Mintile, which improves on it and fixes all of the issues and also allows more functionality like vertical flipping and some transparency and fast fill, things like that. So a lot more functionality coming later on. Now this is the Atari Lynx version, and the Atari Lynx version is a bit irregular compared to the others. Generally the tiles are 8x8 or 8x4 if the graphics are double width, like mode 0 on the Amstrad CPC where the pixels aren't square. But on the Atari Lynx, because of the very small screen, I've decided to use a smaller tile size. Rather than 8x8, we're actually using 6x6. Now this allows for a much larger amount of graphics on the screen, and it doesn't cause the problem of very small representation of the original images, which if we were using 4x4, I'm not sure Chibico would be particularly visible, wouldn't look like the character is supposed to. So that's why I've chosen that size, but it's not ideal because there are some issues that are caused by it. Anyway, let's go over to our code and let's take a peek at what we've got today. So this is the code we're looking at today. This is the Mintile code. We're not going to cover the code that is just very generic, the stuff reading the joystick. We've covered that before. The stuff that reads in the joystick and moves the actual coordinates around. That's the stuff from the simple series. All we're going to look at today is the platform-specific code that relates to the drawing of the tiles. The actual multi-platform code, which is the majority of it, is covered in the Mintile series, which is linked on my website, and there's a separate series of tutorial videos on that. So please take a look at those. Okay, so how do we actually draw things to the screen? Well, as I say, the code that does the sprites and the code that does the background tile map is actually the same code. It's just a question of where we draw. So when we're drawing the entire background, we draw to the screen base. Now the screen base is at memory address C000, that's where VRAM starts. However, our tile map isn't quite the same size as the screen, so we're offsetting by a single byte here to center the tile map that we're drawing. So that's when we're drawing the entire tile map, but when we want to draw just part of the tile map, we're having to calculate the VRAM destination using this getScreenPos function. Now BC is our XY coordinate, and this is in logical units. Now logical units on my tutorials are generally pairs of pixels these days. So one logical unit is 2 pixels and 4 logical units is one 8x8 pixel tile. However, on this system, we're not using 8x8 pixel tiles, we're using 6x6 pixel tiles. And so to maintain the functionality of the other tutorials, one tile is actually 4 logical units, which is 6 pixels, which is a bit irregular, and that's why this is a little bit glitchy. Unfortunately, it does cause some slight graphical glitches at the edges of the screen because the cropping isn't working correctly because of that. And I do have a solution for that, which is to limit the movement to entire tiles. That will solve the problem. And so there's some code remmed out here which will limit the movements to entire tiles. Now, what we're doing here basically, as well as calculating the VRAM destination, now each line of the screen is 80 bytes, so we're multiplying our YPOS by 8 in lines by 80. But first of all, we need to actually calculate the pixel coordinates and byte horizontal coordinates of our drawing. And so what we're doing here basically is we're taking our X and Y coordinates here, and we're effectively multiplying them by 1.5. You can see we're loading in the value here and then shifting to the right here, effectively halving it, and then adding it to the original value. So that's effectively multiplying by 1.5. And we're doing the same kind of thing here, you can see. And then what we're doing with the rest is calculating the maths for multiplying up the Y position by 80. We're doing that. Multiplying by 80 is the same as multiplying by 64 and multiplying by 16 and adding them together, which is a far easier bit shifting operation. So that's what we're doing there, and we're taking the X coordinate here and we're effectively sort of multiplying that up as well. We're centering the screen, we're adding 1 here to the X coordinate, and once we've done all this, the HL pair will contain the VRAM destination, and that's what we need for drawing our objects to the screen. Now, most of the drawing jobs is actually done by the multi-platform code. That's the way we want it. We don't want to rewrite it every time. And so the multi-platform code works out what area needs to be drawn, and then it breaks it up into horizontal strips. And it passes that to the platform-specific code, and that's what we're looking at now. And so we have this routine called doStrip, and that will draw one strip. So it will start from left, draw it to the right, move down, and we just do that repeatedly to build up our tile map or our sprite. So that's what we're doing here. Okay, so do strip first it's loading the X register with 0, and X stays as 0 throughout this, that's used in a few places. And then what it's doing here is it's reading in the tile number from the BCS 16-bit address of the tile map. Now the tile maps are 1 byte per tile. You can see this is the background, and this is the Chibico character. This is our mascot, that character you can see moving around there. It's going crazy. And so that is the miniature tile map that's used for the sprite. Now you'll see some zeros in here, and these are transparent parts of the sprite. A 0 in the tile map is actually a part that is not changed. You see, the tile map is actually a cache of changes. Mintile is designed to work on systems that don't have a double buffer due to lack of memory, and so it's actually drawing straight to the screen, and that means we can't redraw everything every time. We need to work out what's changed and only redraw that. That will reduce the amount of flicker. You'll see little bits of flicker from now and then, but it's minimal, because if nothing changed, nothing's redrawn. And so a 0 in that cache is an unchanged tile. Now we're loading in the tile number here, and we're checking if it's 0, and if it is, we're going to skip over it. If it's not, we're going to process that, and first thing we're doing is we're checking if the tile clear flag is set. If it's set, we're zeroing the entry in the tile map. We would do that if we're drawing the background. We don't do that if we're drawing the sprites, because if we did, we'd lose the sprite and wouldn't be able to draw it ever again, which would be a bit bad. And what we're going to do next is we're going to take the tile number that we've been asked to show, and we're going to work out the offset within our tile data for that tile. Now the tiles are 3 bytes across, that's 6 pixels, and 6 lines down. That's 6 times 3 is 18 bytes. Now 18 as a multiplication, again, a little bit tricky, but we can do that as 16 plus 2 with repeated bit shifts. And so that's what we're doing here. We're calculating the offset for the tile pattern data. And then we're adding the DES pair here, that's a 16-bit address, for the pattern base. So that is the base of the pattern data, and you can see that pattern data lurking around here. Here it is, here's the pattern data. So that is the actual bitmap data of our tiles that we're using to draw our character and our background. Okay, so at this point we've now got the HLS pair is our source pattern data, and when this was executed, the HL pair is our VRAM destination. Okay, so what we need to do is we need to draw 3 bytes for each line and 6 lines. We're now loading the X register with 6, and we're loading the Y register with 0, and the Y register is going to be the offset for the current source and destination of the line. So we're loading in a byte from HLS, that's the source, writing it to the screen, incrementing Y, doing that a second time and doing it a third time. We're then adding that 3 to the HLS source data here. That's selecting the next line of the source pattern data. We're then adding 80 to the VRAM destination here. That's moving us down a line. We're then decreasing our X count, and we're repeating. So that is effectively drawing an entire tile to the screen. Now once we've done that, we're then incrementing the BCS pair here. That is the tile source data here. We're then moving across one tile so that we can repeat if required. So we're adding 3 to the HL pair here, the VRAM destination. That's moving us across one tile. We're decreasing IYL in the 0 page. That is the tile count. IYL doesn't have any specific meaning. These are mimicking the Z80 registers. So IYL is a register on the Z80, and that's the same functionality I've ported across to the 6502. And we're repeating until we've done the line. So that's how we draw the unflipped data. When it comes to drawing the flipped data, we would have a couple of choices. One choice would be to have a second copy of all of the patterns X flipped, but that would take a lot of memory. Another choice would be to flip them in real time. Now that might actually be viable on the Atari Lynx because of its small screen and its fast processor. However, what I've tended to come to do on these systems is actually create a 256 byte lookup table. So we've got this flip LUT here that is being defined as a memory address E800, and the fact that the bottom byte is a 00 there is important because we're going to use that fact. What we're basically going to do is use that bottom byte of the lookup table address as the data that we actually want to convert. So that's our source data that we want to XFlip effectively. So here we're loading that address here, we're loading Y with 0, and we're going to treat Y as the offset and the source byte we want to flip. Now there's 2 pixels in each byte, and each pixel uses 1 nibble, and so we're going to swap those 2 nibbles around, and that will XFlip the 2 pixels within the byte. We've got a routine in our multi-platform common code here called swap nibbles. We're going to run that. That will flip the 2, and so that's effectively swapping the bits like that basically. And then we're storing that newly flipped byte there back into the lookup table offset by y. We're incrementing y until it goes 0 to 255 and then flips back to 0, at which point we're done. So that's our lookup table. Now how do we use it? Well, we use the lookup table in the alternate version of our do strip routine, do strip reverse. It's almost exactly the same as the original, you see. We're loading in our source pattern exactly the same as before. We're calculating our source data in the pattern table exactly the same as before. The only point that we've changed is here. We're loading the B entry in the 0 page with the top byte of the fliplet address. The bottom byte we're loading in from the data from the pattern. So we're loading in a byte from our pattern here, and we're then storing that into the C part with the B part set to the lookup table. And because of the way we've constructed the lookup table, that will point to the flipped equivalent of that C part. And so we're loading in the byte from the BC pair here, offset by X. Now X is 0 throughout the whole of this, so that's just loading in straight from the BC pair there, basically the memory address there. And then we're storing that byte because that is the X flipped equivalent of the byte we read in here because of that lookup table. We're storing that straight to VRAM, and we're repeating until we've done an entire line, moving down a line, and we're repeating until we've done the entire graphic. And that's how we're using that lookup table to quickly X flip our data. And that's the best way I think there is to work with this kind of data. If you X flip it, then if you want to X flip it, then I think we're using a lookup table is generally going to be best, unless you're not using it very much. If you were doing fonts and you had no speed requirements, I guess calculating them in real time, if it was a desktop publishing application or something, maybe there's no priority for speed. But for a gaming application, I think the 256 byte XFlip buffer is best. Now we're going to look at a more advanced tutorial later called MaxTile, which is the successor of this. I've created a more advanced version which uses a 2-byte tile map with more functionality, some clever stuff like fast fill tile, some crude transparency, XFlip, YFlip, X and YFlip. So that's a far more advanced example that we're going to look at later. But this I thought was a good starting point for you to look at, and as I would say, you're welcome to go and to take it from my website, and if you don't like it but you find some parts of it useful, go ahead and take those parts and do whatever you want with them. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.